In this lecture, we introduce another set of flip-flop based circuits which are called the counters. And this is like the not like the ring counter or the twisted counter which we saw earlier. This is exactly what we understand by counters, which is counting numbers. So let us look into the counters. So there are two different types of counting. One is the up counting, another is the down counting. Up counting means you start counting from 0 upwards, 0, 1, 2, 3 like that. However, the 0, 1, 2, 3 is basically in binary numbers where we have to count. That is, we are counting, suppose we are representing the numbers in 3-bit binary, then we are counting 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 and like that. So up to 1, 1, 1, and then the counter must reset itself, right? So after 1, 1, 1 it must again come back to 0. So it is a cyclical counting, it keeps on happening. Okay. So as many flip-flops you will use in the counter, that is the length of the binary word which it can count up to. Now it can all flip-flops can initially start from reset, or it can start from any initial word, it doesn't matter. As you will understand after analyzing the circuit, you can basically start from any given word. However, here we would start from 0, 0, 0 for the analysis purpose. So initially the flip-flops are reset. Supposing that you try to see how the flip-flop states are changing. Now here one important thing to note is that the clock of the flip-flops are not same. Only the first flip-flop is fed by the clock input, actual control input, which is the clock input. Other feedbacks are fed by the output of the previous flip-flop. Here the Q bar output of the previous flip-flop. Okay, and this is positive edge trigger. This is the reason why this is what makes the operation asynchronous, because the change in QB and QC is not synchronized with the clock input anymore, clock edge trigger anymore. It is synchronized with the Q bar edge trigger of the previous flip-flop. But the Q bar, as you understand, will take some time to appear here. So whatever change appears will take some time to appear here, which is the flip-flop delay. So when the clock edge trigger happens, Q and Q bar does not change instantaneously, it takes some time. And when it changes, then with the trigger of Q bar, QB bar also changes, and that also takes some time. Hence QC will also change after some time. So hence the change of QB and QC are not in sync with clock. Hence this is an asynchronous up counter. We first study asynchronous up counter, then we will study synchronous up counters also. So you see here 0, 0, 0 is the initial flip-flop states. Now why does QA become 1 at the first clock edge trigger? Because QA bar is fed back to DA. QA bar, so since QA is 0, QA bar is 1, so this is fed back to DA, so DA was 1. So you see, always we don't write all the signals in the timing diagram, we only draw the signals of interest. However, to get the signals of interest, there may be some intermediate signals which we need to consider. Like here, QA bar, QB bar and QC bar are intermediate signals which actually decide how QA, QB and QC will change. But we have not drawn them, because we can very easily understand what QA bar will be, because QA is here already drawn. So since QA is 0, QA bar is 1, hence at the next clock cycle when the clock edge triggers, QA will become 1. And you see that this QA is independent of QB and QC. This keeps on changing at every clock cycle. Why? because it is always triggered by QA bar. So QA being 1, QA bar is 0, hence in the next clock edge trigger QA will become 0. In the next clock edge trigger QA will become 1. So like this it keeps on toggling. So it is as good as a toggle flip-flop, right? So it keeps on toggling, QA keeps on toggling. But now you see, what about QB? QB is getting triggered. So QB, the change in QB is getting dictated by QB bar, that is true, but the change will happen when QA bar is changing from low to high. So when does QA bar change from low to high? When QA changes from high to low. So you see, when QA changes from high to low, here QB changes from 0 to 1. It will change from 0 to 1 because QB bar was 1. So it is trying to change QB to 1, but it is waiting for QA bar to trigger a positive edge trigger. So here that trigger is obtained and QB is changed from 0 to 1. It will remain 1 unless another positive edge trigger of QA is coming, and the next positive edge trigger of QA comes here, and then it becomes 0 again, and again it becomes 1 at the next positive edge trigger of QA bar, which is the negative edge trigger of QA. So again it changes to 1, and here again it changes. Same thing happens to QC. It is waiting for QB bar to change from 0 to 1. So it is changing when QB is changing from 1 to 0, and hence it is changing now at this instant, and again at this instant it is changing, and between them it is all the same value. So now you can draw up. So you see, again we get 0 0 0 here. That means the same operation will repeat after this clock cycle. So you can end here, and now you look at the sequence you have got. So if you read from QC to QA, you have to read backwards. If you read from QC to QA, you will see that you are counting upwards: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Again you come back to 0 0 0. So the counting has to happen in the reverse order. That is one thing is important. Another thing is important to note, that there is some lag in the clock transition. Hence this is asynchronous operation. What is the lag? The lag of QC will depend on how many flip-flops are before QC. So at any stage the lag in the output, lag with respect to the clock change. The lag with respect to the clock change depends on how many flip-flops are there before this particular flip-flop stage. So this is the up counting operation in asynchronous mode. The same operation can also be achieved by this particular circuit using the JK flip-flop. What is the connection you see? We are basically trying to toggle. That is all we are trying to do. In this D flip-flop we are trying to toggle at a particular instant. So we have to connect JK together to VDD, which is the high voltage, and then give the clocks as we had given in the previous connection also. Clocks are fed from Q bar. So initial flip-flop clock is feeding the initial flip-flop. However, in the subsequent flip-flop, the previous Q bar is acting as the clock. Then the down counter. In the down counter, the connection is same, except that the subsequent flip-flops, the clocks of the subsequent flip-flops are connected with the Q signal, not the Q bar, with the Q signal itself. That means if we start, suppose we start from 1 1 1, okay, all are initially set. Then when QA is changing from 1 to 0, you see here it is changing from 1 to 0 because Q bar is 0, so it is changing from 1 to 0. Now when will QB change? QB is waiting for the change. QB will change to 0 because QB bar is 0. But it will change only when QA is changing from 0 to 1. So this position, at this position 0 to 1, QB is changing from 1 to 0. QC will also change when QB is changing from 0 to 1. QC is changing. And you can construct all these signals using the same analysis. And now if you read from QC to QA, you will see that you are reading downwards, like it's a down counter. That means starting from 111, then 110, then 101, 100, like this you are going till 001, and after 001 again you are getting 111, again you are getting 111. So the cycle repeats. Of course, it can also be set up with a JK flip-flop like this. Only thing what we need to understand is basically the connection of the clock signals of the subsequent flip-flop. The initial flip-flop, the normal clock is connecting. The subsequent flip-flops, which clock is, what is the clock signal there, that is what we need to keep in mind. Okay, so here in up counter, if we have positive edge triggered flip-flops, then Q bar acts as the clock. In down counters, if we have positive edge triggered flip-flops, then Q signal will act as the clock. Then we try to understand some phenomenon here, which is the ripple effect. This is because of the asynchronous mode of operation. What happens? There is this lag in transition of the signals, right? So so what happens when we look here? So when we are trying to change from 000 to 111, then this is changing, so it takes some time to change, and after that change only this will change, and after that change will only this will change. So there is always a lag, right? Though we are denoting it in the same instant as the clock because the lag is very insignificant, but still then there is a lag, there is a definite lag. So while drawing the timing diagram we are not showing the lag, but to do a proper analysis, when we are trying to answer the question of or understand the phenomenon of ripple effect, we have to show the lag, and then only we can understand what is the ripple effect. So here in an up counter we are trying to understand if what is happening when we are changing from 111 to 000. So this first 1 to 0 is happening, and that is triggering the QB's change to 1 to 0, and there is a definite lag there, and then the subsequent lags are happening. What happens then? To change from 111 to 000, the count is basically going through 1111, then 1110, then 1100, then 1000, then 000. This would be 0000, sorry, this is not 1111, this should be 0000. Okay, so you see these three counts are here, which are all spurious counts. These three are spurious counts. These counts we did not want in the system, but it happened because of the asynchronous operation or the asynchronous design. Now normally this is not a problem, because we determine we like observe the signals after some time, after giving it a steady state time to settle down the signals. So normally we are counting 1111, then 0000, but if this count or if this change of, or if these output signals are affecting some other circuit or a system, then after 111 we are expecting 0000 to affect the other system, but the other system intermediately gets affected by these three spurious signals. And this is a problem when we are, so you read this line, this is a problem when these counts are used as control signals for some other operation. Like you have read marks, so if these are acting as marks select inputs, then if they are acting as memory pointers or stepper motor drives, etc., many other operations, this can act as an input, then that becomes a problem. Now, so that is the reason why we need to go to synchronous counters, and before moving to synchronous counters we will understand a bit about the counting operation in order to construct the synchronous counting circuit. Before that, just a pointer here that we can also have a gray code counter, and in the gray code counter it is simply we can connect we can use OR gate, we can use XOR gates at the outputs of an up counter. And by now I hope you have already understood, there was a question in the tutorial how to form a gray code from a given binary code, and you would have figured out that these are the XOR gates which does the trick. We have to connect the XOR gates at the outputs of an up counter in the manner as we have understood. Okay, the MSB remains unchanged, and afterwards every two successive bits are connected to a XOR gate to form the successive signals, successive bits. Now we try to understand what is the up counting and the down counting, what is happening here. So you see these are the 0 0 0 0 0 1 0 1 0, all these numbers, these binary numbers are written in order. So what is happening, the LSB is always changing, you can understand, the LSB is always changing, and it is at every instant, at every stage it is simply inversion of a bit, the operation is inversion of a bit. So basically we are trying to invert whatever is in the input. That inversion is very frequent at LSB, less frequent at the other bits. Lesser and lesser frequency is there for that inversion. Okay, but the main operation is inverting. Also you try to see that this particular word and this particular word are basically inversions of each other. This particular word and this particular word are also, every bit is inverted. So it is like a inversion. So if you start counting from this side, what you see, and if you start counting from this side, what you see are all inversions of each other. This means that if you were working with an up counter and if you had selected the Q bar as outputs, you would get the down counter. So basically you did not need to reconstruct the down counter, you could have simply taken the Q bar outputs and you would have gotten the down counting operation. Similarly, if you have the down counter and if you had selected the Q bar outputs from the down counter, you would have got the up counting. So this is a very useful thing when you are working with up counters and down counters. So you don't need basically two different counters. You can use the same circuit as up counter or a down counter depending on which output you are taking. But more useful is to understand this thing. So this is when we are moving from normal counters to synchronous counters. We understand how the counting operation takes place. When does the bit change? That is what we are trying to understand here. When does the bit position, when does the bit toggle? So we note by looking at these numbers, we note that we have noted that the bit at position k toggles only when all k minus 1 bits starting from the LSB are 1. This is for up counting. Similarly, for down counting, the bit at position k toggles only when all k minus 1 bits starting from the LSB are 0. Read the statement and look at the numbers. Up counting, a particular bit at, so the LSB will always toggle. So please keep this in mind, the LSB will always toggle at every clock frequency, at every clock edge trigger. LSB will always toggle. What about the other positions? The position number 1, suppose position number 1 is will toggle when all k minus 1 means all 0 bits starting from LSB are 1. That means the LSB, when it is 1, the position number 1 will toggle. So when the LSB is 1, at this place LSB is 1, so at the next instant the first position will toggle. When all the bits from LSB up to 1 are 1, then the position number 2 is toggling. Similarly, if there was a position number 4, it would have toggled here from 0 to 1 because all the previous bits are 1. So you can think it in this way, all the previous bits or the lower order bits are 1, then the present bit will change from 0 to 1. Similarly, for down counting, if you look in this way, in this direction from right to left, for down counting, when all the a position will change, so here from 1 to 0 it is changing when the LSB is 0. Similarly, here this change, you see this change happens from 1 to 0 only when both the previous bits are 0. So we keep this in mind. And that will give us a directive to construct the synchronous counter. Now you look at the synchronous counter. So what is the thing? We have to toggle only when all previous bits are 1. This is for up counter. We have to toggle only when all previous bits are 1. So why not use the previous bits to toggle my flip-flop? That is exactly what has been done. The first flip-flop will always toggle. That is, we have to connect it with the VDD. It is always toggling. At every clock cycle it is toggling. But the next flip-flop will toggle only when the previous, so QB will toggle only when QA is 1. QC will toggle only when both QA and QB are 1. So you connect QA and QB with an AND gate and then pass it, connect it to J and K, tie it up with J and K. And the toggling we have to change all the signals at the same time. So we connect the same clock with all the flip-flops. Now it becomes a synchronous counter, synchronous up counter. It becomes a synchronous up counter. And you can try to draw up the timing diagram and you will find the same timing diagram. We actually don't, you can very easily write it down without even analyzing. However, I will suggest or I will urge you to analyze whether the timing diagram for this particular circuit is what has been given here, just for verification. Once you verify, you will always remember how to construct this circuit, and this is the timing diagram associated with it. Very easy and straightforward. Down counting operation, what we need to do? We need to change the AND gate, you see. So we need to toggle. We are still doing the toggling, right? We need to toggle when the previous inputs are 0. QA and QB are 0. So QA and QB are 0 means QA bar and QB bar are 1. That is what we are trying to catch here. So Q bar is what we are connecting with the AND gate and then feeding to the JK, tying it up with the J and K. So Q bar is what we are tying up with the J and K. Okay. So this is how the down counter is constructed. So here please keep this in mind, always give the jumpers when you are drawing the circuits. Here I have not given the jumper because of simplicity of drawing these circuits digitally, but you when you are drawing the circuits in pen and paper or pencil and paper, you always give the jumper, otherwise it is a bit difficult to understand. Okay. So this is about the down counter operation, down counter, synchronous down counter. Very easy, and you please verify whether this circuit leads to this timing diagram. Now there are counters which can both act as up counter or down counter. Obviously, if you know that if you are taking QA as down counter here, so Q bar will act as the up counter. But here we have done a fancy thing actually. So we are trying to take only QA, QB, QC and make it as up counter or down counter. So we have some additional gate circuits here. So what is happening here? So when we have connected this position, this bus, this particular bus with VDD, then this is connected with 1 here, and this is connected to 0. So all the outputs of these lower AND gates will become 0. Okay, but the outputs of the higher AND gates will get dictated by QA. So here it is by QA, and then this QA will pass here, and in QA and QB. So this is almost like, this is like the up counter, right? This is like the up counter, and this is getting all the flip flops are getting triggered as per what is the state of the previous flip flop outputs. When all the previous flip flop outputs are 1, then the present flip flop output will change. And you see the first flip flop is connected to VDD, J and K are connected to VDD. Now if this bus is connected to 0, connected to ground, then what happens? These upper AND gates are all giving 0 output, and the lower AND gates are getting activated. So it is like now the down counter operation happening. So this switch decides whether you are having an up counter or a down counter. So this is the timing diagram. I think this is for the down counting operation, the timing diagram. Yes. So when you connect with as an up counter, your timing diagram will change. The next important thing is the mod n counters. So one very specific modern counter is the BCD counter. BCD counter is, it is counting the BCD digits, which is the 4-bit binary blocks from 0000 to 1001. We don't have numbers from 1010. That means whenever 1001 is coming, at the next count must be 0000 again. We must come back to 0000. But normally if you construct a 4-bit counter, you know that it will count till 1111 and then come to 0000. So what we have to do, we have to make an intermediate circuit so that whenever the output is 1001, at the next instant or at the next clock cycle, my output should be 0000. How to do that? We in this particular circuit that we have drawn, we are utilizing the clear signals, preset and clear signals basically. So here I am showing the clear signals. So whenever the output is 1001010, so before that, at no other situation, this NAND gate will give you a 0 signal out. So NAND gate is connected in that manner. So whenever the NAND gate is receiving 1001010, so you see 1 0 1 0, only then you are having a low output at the NAND gate. Before that, at no other condition, you will have a low output at the NAND gate. So NAND, when is the output of a NAND gate low? When all the inputs are 1. So are all the inputs 1? When it is 1010, verify 1. This is 0. This means this is 1. This is again 1. This is 0. This means this is 1. Yes. So all the inputs are 1, and in any other word before 1010, all of the inputs will never become 1 at the same time. That means the NAND gate will trigger a 0 to the clear signals which are active low only when you have generated a 1010. What it means? As soon as you generate a 1010, your flip-flops will get reset. So the 1010 is happening for a very short instant. Though it is present, it is happening for a very short instant. So for the full length of the clock cycle, you are only getting counts from 0000 to 1001. At the next clock edge trigger, it is becoming 1010, but instantly it is becoming 0000. So basically here the clear operation or the resetting operation is asynchronous. Though the circuit is synchronous, the counting is synchronous, the resetting operation is asynchronous. And it is easier to draw a circuit with asynchronous resetting operation. That is why I have drawn here asynchronous resetting operation. You have to keep in mind that you have to also provide a high preset along with a low clear. That high preset can be easily generated by putting a NOT gate at this end, at a NOT gate here, and then connecting that to all the presets. That is not shown here, and that is not needed to be shown also. This is understood that if you are giving clear 0, you are also giving preset 1. That is understood. Now a general mod and counter. What are mod and counters? This is BCD is basically a mod 10 counter because it counts 10 number of digits. A mod n counter will count n number of digits starting from 0 and ending at n minus 1. So BCD is a mod 10 counter. So these counters can be synchronous and asynchronous. The counting operation can be synchronous or asynchronous. It doesn't matter. The resetting operation can also be synchronous and asynchronous. Here we have shown a asynchronous resetting operation. And here we need to, what about the resetting operation? The logic circuit we need to make, so that when the outputs of with the outputs, so that the flip-flops are cleared when the count reaches a particular output count. We need to clear the flip-flops when the count reaches a particular output count. Now what about this particular output count? In case of using asynchronous clear input, this count should be n, as you already observed. When it is 10 10 10, only then it is clearing at the same instant. However, if you are trying to design a synchronous clear input, we should not say synchronous clear input, but we should say, if you are trying to design synchronous resetting, we should say like this: if you are trying to use synchronous resetting, then you should clear flip-flops at the next clock edge cycle, and the count with which you are trying to make the logic circuit should be n minus 1. That means in this particular case, when you have already formed 1001, which is coming at the output, you should have formed a logic circuit which gives you a reset signal with this input being 1001. But that reset signal should not be connected to the clear signals, these asynchronous clear signals. Where they would be connected? They would be connected at the inputs j and k through some logic circuit. Like you can understand, I can connect an AND gate and pass that 0 to this AND gate. This signal will be 0 only when the output is 1001. So at the next clock cycle, this 0 will pass to the QA. Similarly, this same 0 can be connected by an AND gate to J, JB, JC, JD also, and the complement of it would be connected to K. So it would be connected via NOT gate to K. So there will be an AND gate here, and this same signal will be connected after passing through a NOT gate to this input of this AND gate, K, KB, KC, KD. So what would happen then? When you are having the signal 1001 at the output, you are forming a 0-1 situation at the input of the JK of all the flip-flops. You are forming a 0-1 input at the inputs of all the flip-flops. So at the next clock cycle, this 0-1 will trigger all the flip-flops to become 0, outputs to become 0. And then again the counting will start from 0000. And because at no other counts other than 1001 this is going to trigger, so after this, at every instant this would be, the J will become 1, okay, and K also has to become 1, so K must not be 0. So you have to actually do some more complicated circuitry at K, and that is what makes it a bit complicated to design a synchronous resetting. So normally we go for asynchronous resetting if we don't have very precise operation required. Because to avoid the complicated circuitry at the input side of the flip-flops. Okay, but if it is required, then you have to think about that circuitry and implement that circuitry at the input side of the flip-flops also for synchronous resetting. But normally we go with asynchronous resetting if such precise operation is not required. So that is the story about mod n counters and synchronous resetting and asynchronous resetting. Thank you for your attention, and this ends our discussion on counters. And from next lecture we would start to actually develop sequential circuits given a particular problem statement. So these circuits, these are also sequential circuits, But these are very standard circuits, like the adders and adders, subtractors, those circuits are standard circuits. These are also standard circuits. But after this, we will try to make a new circuit. Any new circuit can be made given a particular problem. That is what we will see in the from the next lecture. Thank you for your attention.